Start. So we're going to talk about the nature of matter. Okay. So we've looked at. So we watched a video called, if you remember, Atoms Clash of the Titans, where they talked about, the atom itself and how really it's quite mysterious and it's not exactly the easiest thing in the world to visualize. So we're going to talk about atoms, and we're going to talk about, what are atoms made out of. Some of it will be review, but some of it will be new. So here's a picture of the universe. Okay. And I'm going to come back to the universe. I'm going to talk about actually what makes up the universe. Okay. There are 3 important ingredients that make up the universe. You learned this, right? A long time ago. You're probably still in diapers. All matter is made up of atoms. Okay, good. And you probably learned about the building blocks of the atom, right? All right. So what is found in the nucleus of the atom? Okay. What's similar about them? Their size. But what's different is protons are charged, +1, positively charged, whereas neutrons are neutral. And then what zips around the nucleus are those things called the electrons, right? So you probably learned that atoms are made up of protons, electrons, and neutrons, right? Now, of those 3, only one of them is what's called a fundamental particle, which means it's not made up of anything else that we know of. Maybe it could be, but as far as we know of, it's not made up of anything else. Like an atom is made up of protons, neutrons, and electrons. One of those 3 is only made up of nothing else but itself. Like you can't divide it anymore. Do you know which one it is? No? Okay. We'll come back to the answer. So it's actually, in other words, 2 of these 3 particles can actually be broken down into even smaller particles. Okay? All right. Now, you saw in the video Clash of the Titans that physicists have to use tools, equipment, to study atoms, right? So what did Rutherford use to study the atom? Yeah, he used a thin sheet of gold foil, and then he used a gun that was spitting out radiation, right? And he used detectors to see the impact. Already sent down. Okay. So tools. This is a picture of the largest tool, largest machine ever built by humans to study, in this case, physics, to study particles, to study the nature of matter. This is called the Large Hadron Collider. It's what's known as a particle accelerator. There are many of them out there. Okay, this is the biggest one. Supposedly, China is building one twice as big. I don't know when it'll be ready. Supposedly. I don't work for these guys, so I have no idea. I just heard this morning about that. I was watching a video about this. This particle accelerator came online in 2009, but it was being planned decades before. Okay, so it's been in the works for a long time. The number 27 represents the circumference of this machine. It's 27 kilometers in circumference. It's on the border of France and Switzerland near Geneva. There are over 10,000 scientists and engineers that have worked together on this project. So it's quite the endeavor. It's underground. It's about 150 meters underground. And it uses these really, really powerful magnets. Okay? Very powerful magnets. These magnets, they're cooled down to basically 2 degrees above absolute zero. Absolute zero is minus 273. What these magnets do is so I said this is called a particle accelerator. So guess what they do? They accelerate particles. What they do is these magnets accelerate particles in the opposite direction. So they crash into each other. you want to understand what's inside something, sometimes you got to break them apart. So that's what these things do. They collide particles to see if they can detect new particles. They will accelerate these particles at almost the speed of light. You can see it's 99.999999% the speed of light. Speed of light is about 300,000 kilometers per second. So this is about 11 kilometers per second shy of that. But even at this rate, you're looking at going around the world 8 times in 1 second. So think about that's fast. That's really fast. At that speed, when these particles collide and they smash, sometimes they produce new particles. And sometimes these particles can be observed. This is a detector, okay? You can see, by the way, how big this detector is. There's a person on the bottom, right over here. So you can see it's a massive object. It weighs like many times like a jumbo jet. It's huge. I think it's like 2,500 elephants in weight. Oh, wow. I think. Don't quote me on that. So it's big. And this thing is like, think of it like a camera on steroids. So as these particles collide and they release maybe other particles, these cameras are taking like millions of images per second to detect anything that's new. So they're looking for new particles. They're testing out the laws of physics. So going to a picture like this is a picture of the atom. Now, you know, again, the real picture of the atom is a lot more mysterious. But, you know, let's talk about a simple picture of the atom. You know that there's a nucleus. You know that around the nucleus there's the electron. But what was discovered by smashing things together is that protons and neutrons are not fundamental particles. They're actually made up of 2 other things called quarks. And one's called an up quark, and the other one's called a down quark. And you can see the color here, green. No, actually, there's 3 colors here, though. 3, green, blue, and red. So this actually is, you can think of it as like the fundamental particles that we see in matter, okay? And you're probably not familiar with most of them. I mean, you learn, again, remember, you always learn the simple stuff first, right? You learn atoms are made up of 3 things: protons, electrons, and neutrons. It's more complicated than that. So this is what makes up matter. You'll notice, you'll recognize maybe a couple of terms. You definitely in the bottom left corner recognize the electron. So it's there. It's one of the ingredients of matter. But you don't see protons and neutrons. It's not one of the fundamental particles. But these 2, the up and down quark, they make up protons and neutrons. And the difference between a proton and neutron is the ratio of one versus the other. So a proton has 2 up quarks and 1 down quark. Because if you look closely, an up quark has a charge of plus 2/3. So if you do the math, two-thirds plus 2/3 plus negative 1/3 equals plus 1. So a proton has 2 up quarks, which are both plus 2/3, and 1 down quark, which is negative 1/3, and that adds up to plus 1. And what's the charge of a proton? It's plus 1. Whereas a neutron is 1 up quark plus 2 down quarks. And that adds up to 0. Because what's a neutron is neutral. Don't worry about this chart. You don't have to memorize all of the different things that make up matter, okay? We will talk about some other particles in here. Like, we will talk about these neutrinos because they're important when it comes to radiation and radioactive decay. Okay, we are constantly being bombarded by neutrinos, but you don't feel them because they're so tiny. So these first three columns are what make up matter. All right. On the right, the things in red, those are the particles that are responsible for force. So you've heard of like electromagnetism, right? You know that magnets attract and repel. So the photon, which is this thing here, is the particle that transmits that force. The photon is also the particle of light. And if you take physics, you'll learn that light and electromagnetism are strongly related. Okay? They're actually the same thing, but you'll learn about that more in physics. Below that is something called the gluon. Now, think of its name. So do you think it holds things together or repels them? It holds things together. If you think about the nucleus for a second, you recognize it's a problem, right? You have protons in the nucleus that are positively charged. You've got things in the nucleus that are positively charged that are very close together. What should those things do? They should fly apart, but they don't, because the gluon holds them together, right? And in a nuclear reaction where the nucleus breaks apart, that is overcome, and all the energy is released. Then the bottom two are particles that allow for atoms to change into other atoms through what's called radioactive decay. Okay, and we'll talk a little about that later on. So you can see this is called a standard model particle physics. There's been an addition recently. One of the reasons they built the LHC, this big monstrosity, was they were looking for this particle called the Higgs, which is known as the God particle. All right, because you learned a long time ago that matter, okay, it's made up of atoms, but you learned that probably that matter is anything that has mass and takes up space. And I think I asked you a few days ago, well, what exactly is mass? So the proposal was that there's a particle, like something called the Higgs, named after the researcher who proposed it. Just like there's a particle that explains magnetism, the photon, there's a particle that's got to explain mass. Because some things have a lot of mass, something like light has no mass. So the particle that was proposed is called the Higgs. The LHC discovered it in 2012. So the Higgs now is part of this standard model. And what the Higgs proves, now this is going to get a little bit weird, H-I-G-G-S right there. What the Higgs proves is that there's this thing called a Higgs field. Now you're like, oh my god, I'm losing it now. I'm going to start falling asleep on this guy. I can explain this really easily, okay? So what the explanation for mass is, you don't have to explain this on a test or quiz, but it's interesting in the conversation, okay? When I say the word field, what do you think of? Yeah, like somewhere you play, right? So it's, you think of a space, like a space. Think of the word space. Field, space, same thing. The gravitational field is the space where you feel gravity. The electromagnetic field is the space where you feel electromagnetism. The Higgs field is the space where this Higgs particle is interacting with other particles to give them mass. Let me give you an analogy. This is not my analogy to explain how it works. So if I say to you, what's mass? This is the analogy that I heard, which to me is a really clever analogy. It's not my own, so I'm not going to take credit for it. Things that are massive are things that really strongly interact with the Higgs field. Things that have very little mass or no mass hardly interact with it. So let me give you an analogy to explain that. Let's imagine the Higgs field is like a space, like a party. So the party going on. Okay? Lots of people in the party. And then I asked my last class, give me someone who's popular. I said Drake. Okay, Drake. So give me someone who's popular. Drake. Someone that everyone would know. No one knows Ashley. So Drake walks in. Now imagine Drake's job is to go from one end of the room to the other end of the room, but there's a huge crowd. What's going to happen as a popular person walks into the room? It's going to be surrounded by people, right? They're going to ask him for his autograph. They're going to want to talk to him. Do you think it would take him a long time to get to the other side of the room, or think can he really whip through quickly? A long time. Because you can see there's a very strong interaction between him and the people in the crowd, right? So he would be like something that's very massive. Because there's a very strong interaction with this field. But imagine someone who's not popular, like me. I walk into the room, no one gives a rat's ear. I didn't swear.
I did.
I can walk into the room, freely move around. I'm not hardly interacting with the crowd at all. So something that does not interact very strongly with the field, something that have very little or no mass. So now there's an explanation for what mass is. Mass is an interaction with this field. Strong interaction, it's massive. A weak interaction, not as massive. Right. So each atom has a particular interaction with this field. So it is an interesting and clever explanation. No. You don't have to explain it. It might be like a multiple choice trivia question, but you don't have to explain it. So it would never be like a short answer question, explain the Higgs field, but it could be like true or false. A massive object is something that weakly interacts with the Higgs field. The answer would be false. You learn about this stuff, right? You learn the atomic theory, Galton's atomic theory. You learn that. Now all of this refers to what kind of reactions that we cannot destroy, create atoms. So if you take magnesium and you burn it, it reacts with oxygen. Okay? So you take magnesium. You ever seen that one? That reaction? Okay, you take magnesium and you react it with oxygen. You get something called magnesium oxide. And here, I'll balance it for you. But we'll talk about balancing later. Okay? But here's the thing. In this reaction, we didn't destroy atoms. We didn't create atoms. The amount of matter the mass is the same on both sides. This is called a chemical reaction. So in a chemical reaction, the law of conservation holds. But in a nuclear reaction, it doesn't. So a nuclear reaction is, for example, what's going on in the sun. The sun will take hydrogen and fuse it into helium, and you get a new particle. You get something new. In that case, some of the energy is actually, some of the energy that's being released by the sun comes from mass. So in a nuclear reaction, and again, you don't have to explain that. In a nuclear reaction, you actually do lose mass. You do create new particles. Okay? And there's a very famous equation that captures that. E equals mc squared. This equation actually shows you that energy and mass are actually connected. They're connected. They're basically just two sides of the same coin. Those particle accelerators, when they collide those molecules at very fast rate, some of the energy is converted into mass. So you create these new particles. So yeah, you can change the mass, but that would be a nuclear reaction, not a chemical reaction. So here's an example of a nuclear reaction. We will look at this in more detail. Okay? So, what's going on with carbon? What's happening to it? it's becoming something different. It's not the same atom anymore. Now it's becoming nitrogen or boron. So that would be an example of a nuclear reaction, not a chemical reaction. Okay? And we'll explore that in more detail. So you learned about the atomic structure, right? So you were doing an activity on the periodic table. So trivia question, what is the atomic number of a substance? Is this what? What is it? Number of protons, right? Every element has a specific atomic number, right? So that means every atom of the element has the exact same atomic number. So what would be the atomic number for nitrogen? 7. What would it be for boron? 5. Okay, so every boron atom should have 5 protons. Now, the mass is different. The mass number is not just the number of protons, it's the number of protons and neutrons. So, what would be the mass number for the carbon atom in the top left corner? It'd be 14. What would be the mass number for the carbon atom in the bottom left corner? 10. Okay? It's the number of protons and neutrons. So if two things have different atomic mass but the same atomic number, what are they called? Called an isotope. So here, an isotope is something that it's the same element but doesn't have the same mass. So here, carbon 14 and carbon 10, they're isotopes. Same element, but they don't have the same mass. Okay? Here are other examples. So here's carbon 12, carbon 13, carbon 14. To be honest, I don't even know if carbon 10 exists. I guess it does. I've never ever heard of it, but I'm sure it exists. Okay. You learned about ions? What's an ion?
Charged atoms.
So if an atom gains or loses electrons, that means the number of protons and electrons are not the same anymore. So a cation, Catherine, is, would a cation have gained or lost an electron? It's positively charged, so that means it lost an electron, whereas an anion would have gained an electron. What about an onion? Very good. So, did you guys draw these in grade 9? Okay. What do these represent?
Moving the nucleus, the yellow stuff is electron, and the black line is.
Okay. Now, to be honest with you, if you're trying to describe where the electrons are, you know that's more complicated than this, right? The atom itself is more complicated. The description of where the electrons are take different shapes. They could look like dumbbells, for instance, or they could look like circles. So they don't look like rings. No, don't worry about that. I'll tell you what's important. But so where these electrons live, okay, they're not really drawn like this. But this is a good representation for what are called energy levels. Because the idea is, if an electron has a certain amount of energy, so you can see in this picture over here, an electron, here's the nucleus, so here's the electron right over here. If an electron, so here it's in a certain level called K, okay? And that you can see, it's represented as a step. And if you think about an electron that's in level L, it would actually have more energy than the electron in level K. And then the electron in level M has even more energy than the one in level L. And N would have even more. Think about yourself. If you had to walk up the steps, you would have to put energy in to walk up the steps. So the electrons at these different levels have different energies. And you saw in the video that when they jump down, they release color, right? And they don't have to jump. They don't have to jump from N to M, and then M to L, and L to K. They can jump from N all the way to K. They can jump from N to L. So there's different combinations which will give you different colors. Okay. So these represent the energy of the electrons. Okay. Now let's talk about the periodic table, because all of these atoms. So we talked about atoms and what atoms are made out of. You know that they're organized in these things called periodic tables, right? And you know kind of already, because you're doing an assignment on this, you know how this is ordered, right? Like, what determines the ordering of these elements? What is it? Is it their mass or their atomic number? It's their atomic number, right? So hydrogen is the first element because it has 1 proton. Lithium is the third element because it has 3 protons, right? Okay. And you know that this is also organized into groups. Okay. What we're going to do is we'll talk about trends in that table, because you already know a few things about this table. Like, for example, you know that on the right side we have these things called the noble gases, and true or false, they're highly reactive. No, they don't react. Okay, they don't react. And you know that the metals are on the left side, and as we go to the right side, you have gases. So you know some of the properties of these tables, right? I want to talk about trends in the table. So we're going to talk about the size of the atom. We're going to talk about something called ionization energy, and we're going to talk about something called electronegativity. And this is our last topic, okay? But I'm going to ask you first, I want you to think of something. Actually, no, I'm going to ask you to think about that after I show you this picture. So this is a picture of the size of the atom. So the size of an atom would be basically, if you think of the radius of the atom, it would be from the nucleus to where that last electron is. Okay? We're going to ignore the noble gases, because if you look at the title of this chart, it says covalent radius. That means that the atom is bound to another atom. But noble gases don't react. So they don't. So we're going to exclude them from our little talk right now. Because we're going to talk about the trend that you see in terms of the size of the atom. So remember, ignore noble gases. This is going to throw you off, because they don't react, so we're going to ignore them. What trend do you see as we go from left to right in terms of their size? It gets smaller. You see that trend? It gets smaller. There are exceptions. When someone says it's a trend, that means no, it's not. It's general. It's a general march in a particular direction. What about when you go down the table? It gets bigger. Okay. Now, question is why? So let's think about an atom like lithium. Okay? So I'm going to draw you lithium. So here's lithium. Here's the nucleus of lithium. You learned in grade 9 that you can draw 2 rings around lithium, right? Okay, so I'm going to draw 1, and I'm going to draw 2. So we know that there's 2 electrons there, and there's 1 occupying an outer shell, right? And the shells don't look like this, though. The shells have different shapes. So I'm going to draw like this just so it's easier to understand. Now, fluorine is in the same row, right? So the same row. So the second row. It also has 2 rings. And these are really, really ugly pictures. And we know that fluorine has 7 electrons in the last shell. But if you look at the picture of fluorine, it's a lot smaller. Why? So If you look at lithium, lithium has 3 protons. So the charge of the nucleus would be +3. But if you look at fluorine, fluorine has 9 protons. In other words, the nucleus is +9. So which of the two have a stronger nucleus? This one. Now, they both have the same number of rings, but fluorine has a much stronger pull on the outer shell than lithium does. So what happens then is fluorine will pull and make those electrons coming closer. So as the nucleus gets stronger, the electrons come closer to the nucleus. Now, that explains, as we go from left to right, why the atom shrinks in size. Because the nucleus gets stronger, and there's a stronger attraction on the electrons, and it pulls them tighter in. Okay? But why does the size increase as we go down, though? So let's look at an element below lithium. So here's lithium over here, and there's sodium right below it. Okay, you know sodium's bigger. Okay, let's think about sodium now. So if I was to draw sodium, can I erase fluorine for a second? Let me erase this. Okay, so let's draw sodium. Okay, so here's sodium, and here's the nucleus. Sodium's got 1, 2, 3 rings. Now, we know how to fill these in. You learned about this in grade 9, I believe. Okay. Sodium and lithium both have, they're both metals. They both have 1 electron in that last shell. But here's the big difference, though. The nucleus of sodium has 11 protons. So it has a much stronger nucleus than sodium, right? But it also has an extra ring, or an extra orbit. You see this electron over here? You see how this electron would be affected by these 2 rings on the inside, whereas this 1 electron is only being affected by 1 ring. This is being affected by 2 rings. That's called electron shielding. So you can see the problem here. Even though the electron is being pulled by a stronger nucleus, it's being repelled by more electrons on the inside. So if you have to think about this, there's 2 things that affect the size of an atom. One is the strength of the nucleus, and the other one is how many electrons there are in between the outer electron and the nucleus. So things with more rings or shells will have more repulsion, and they'll be further away. So that's what you're seeing here. You're seeing, as we go from left to right, the nucleus is stronger, so the electrons are being pulled closer together. But as we go down, there are more electrons inside that are repelling the ones on the outside. So the atom gets bigger, even though the nucleus is stronger. Does that make sense? Now, that's related to the next one, ionization energy. So the ionization energy is how much energy it takes to remove an electron. So let's think about this for a second. What do you think? You think it would be easier to steal sodium's electron or lithium's electron? Why? Because look at the position of the electron. They're both by themselves, but I'm not drawing this to scale. But the idea is that this electron is much further away than this one. So even though sodium has a stronger nucleus, the electron, the outer electron, is really, really far away, that it's easier to actually steal that electron than it is to steal the electron from lithium. So the easier it is to steal the electron, then the lower the ionization energy would be. So if you use that logic then, as we go to the right, the ionization energy should what? What do you think? It should increase, because as you go to the right, the electrons are moving what? Closer to the nucleus, and they should be harder to steal. And as you move down, the electrons are moving further away because there's more electrons on the inside repelling them, so they should be easier to steal. So the ionization energy will increase to the right and decrease as we go down. Okay? Again, and this is all related to the way the atom is structured. The last one is the electronegativity. Electronegativity, which is the affinity for taking an electron. Okay? It's rated, oh, by the way, here's the image for ionization energy. You'll notice the highest ones are helium, neon, argon, krypton, xenon, radon. Where are they all? They're all on the right side. Okay, so this is the highest electronegativity, but as you go down, the ionization energy goes down too, because it becomes easier to take the electron. The last thing is understanding electronegativity, which is the ability to take an electron. So this is a chart. Now this chart is this is your periodic table. So this over here, this is your left side, this is your right side. So you can see, oops, sorry, you can see it. You can, whoa, what happened here? Sorry. It's out of 4. 4 is the highest. So the higher the number, the more the higher the affinity for taking an electron. It's like if you think of a tug of war, it has a stronger pull on the electron. As you move towards 0, you have a weaker ability to get an electron. So you can see that the low electronegativity is on the left side, and the higher ones are on the right side. Now, question is why? Let's go back to our picture, okay? Why would one atom have a higher electronegativity than another atom? So I'm going to draw 2 atoms for you. I'm going to erase this. Okay. Here we go. I'm going to redraw fluorine. But I'm not going to draw the rings. I'm just going to draw the nucleus and the outer electron, okay? So I'm just going to draw the outer electrons, and they're sitting probably... Actually, no, I'll just draw them both. What's the difference at this point? Okay. Now, let's draw... What's the second element after fluorine? So there's neon, and the 11th element would be what? Sodium? So let's draw sodium. Okay, here's sodium. Now, why does fluorine have a stronger electronegativity, or higher, than sodium? Okay, so let's draw sodium. Isn't it bad? It's so bad. Oops. I put an extra. Relax, I caught that. And it's on video too. Okay, so I'm just drawing in. Oh yeah, I gotta work on this. Okay. So, fluorine, if you look at the electronegativity of fluorine, it's close to 4, whereas sodium is 1 point something. I can't remember the exact number, but it's smaller. Now, why is it? Because sodium has a stronger nucleus. The nucleus of sodium has 11 protons. The nucleus of fluorine has 9. But why does fluorine steal an electron from sodium, not the other way around? Okay, I know, but atoms don't make up their minds. Okay, but why? Let's take a look. So, when these atoms come close together, so if I was to move fluorine towards sodium to make sodium fluoride, think about this electron. This electron, would it be more attracted to sodium or fluorine? Yeah. Even though that electron belongs to sodium, it is so far away from sodium that when fluorine approaches, the nucleus of fluorine will be closer to the electron than the nucleus of sodium. And therefore, it would pull the electron into, well, I would pull it here somewhere. Okay? So, you can use the understanding of like the size and the strength of the nucleus and to understand why the electronegativity goes up as we go to the right, it goes up, and it goes down as we go down the periodic table. The electronegativity goes down because the atom gets bigger and bigger and bigger. Okay? So, we talked about the atom. Oh, my Lord, I forgot to mention something really interesting. Yeah, okay. So, anyways, I'm gonna go back to something. So, we talked about the nature of matter. We talked about the Standard Model. We talked about trends in the periodic table. I did forget something that's quite interesting. Because I added it this morning, and so true, false. Protons are a fundamental particle of atoms. False. Electrons? Are electrons? Are electrons? Well, yes, they are. They're right here. Electrons are one of the fundamental building blocks of matter because they're in this table, but not protons and neutrons. I forgot to mention this. I started with this picture, right? Of the universe. That's what I forgot. All of the matter that you see in the universe is only 4% of the universe. In other words, the universe is only comprised of 4% of the universe is matter. The other 96% is something else. It's dark matter, which is 27%. That's matter that you can't see. That's why it's dark. And they know it's there because it would be like, imagine it put something on a scale that I know weighs 1 kilogram, and I can see it's a 1 kilogram mass with my eyes, but the scale says it's 10 kilograms. And the scale works, because I know cats can say the scale doesn't work. So the scale works, so I know that there's something that I can't see that is affecting this scale. So dark matter is matter that we can't see, and it's about 27% of the universe. And there's almost 70% of the universe which is called dark energy. And this was discovered because you guys have heard of the Big Bang theory. The idea that the universe started off as a little point and exploded. And people thought that eventually what would happen is everything will come back into the big crunch. But then it was discovered that the universe is actually accelerating away. So the explanation for the acceleration is this thing called dark energy, which is causing this repulsion, which is acting against gravity. Because gravity should slow everything down and pull it back together. So we were talking about the nature of matter, but I want you to understand that matter only makes up 4% of the universe. Okay? And we'll end there. The end.